So an example is calculate flux across, so here we're going to get a surface, the upper hemisphere of the following. And we have x squared plus y squared plus z squared equals 1. And this tells us, this is also given, oriented, here's our orientation specifics, right, with outward pointing normal vectors. I'll just write, okay, normal vectors, and this is the important part too. Well, I mean, all of it's important. So the vector field is z, x, 1. All right. So this is how we're going to approach it. So we have some, I'll draw a little picture here. So we have some hemisphere. So so here's our x, y, and z. So we have a circle here. Okay, great. And then our hemisphere looks something like a bowl, like a dome, right? Okay, and they cross at 1 at all of the axes because it's a unit sphere, you could call it. Okay, so here's our surface, and that's pretty much it. There's no bottom to it. And it says oriented with outward pointing normal vectors. So we're calculating the flux. So you can consider flux as like something flowing through the surface a little bit. I don't know what it is. Maybe it's like wind or water or whatever. But in this case, we're doing the flow of something out of the sphere. So outward pointing normals. Do you see this? So something like that. That's the whole concept here. So step 1, what we're going to do, so step 1 is parameterize your surface. Parameterize a surface. Okay, so here we're dealing with a sphere, right? So we need to use spherical parameterizations in a sense. So the radius of the sphere is going to be constant, right? It's going to be a constant 1. So r, I guess I'll just say r equals 1, and that's constant on our surface, right? We're just touching the surface, so it's just going to be 1 all the time. And then our variables, our parameter variables, are going to be phi and theta, okay? And if we recall, our parameterization for a sphere is the following. So we have g of phi and theta, and that's going to equal our radius, so that's a 1, times cosine theta sine phi, and sine 1, sine theta sine phi, and 1 cosine phi. All right? So from here, we can just calculate the tangent, the tangent vectors. So with respect to phi, that one is going to be, we get a cosine theta, cosine phi, and then we get a sine theta, cosine phi, and then a negative sine phi. Okay, and now for the tangent vector with respect to theta, and we're going to get a negative sine theta, sine phi, a positive cosine theta, sine phi, and the last component is just going to be 0 because there's nothing in terms of theta here, right? Okay, so we have our tangent vectors, and now we need to take the cross product to get our normal vector. So, taking the cross product, as I've said in the concepts video before, that's very lengthy for such a problem, but if you remember, which I would recommend that you try to remember at least, the formula for the normal vector of a parameterized sphere is r squared sine phi times your unit normal, which is cosine theta sine phi, sine theta sine phi, and cosine phi. Okay, so if you'll see here, this is basically everything in like the arrow brackets, this part, that's everything except for your r's in your original parameterization of the sphere. So you can just like take out the r's, and that actually appears here. But anyways, so this is our normal vector, okay? And And here you could just like get rid of this one. It can be invisible. And then the next thing that we need, so we have our normal vector, so that's good. This is our n of u and v, but in this case it's phi and theta. Okay. And now we need our f, our vector field, which was equal to z, comma x, comma 1. This is going to be what in terms of phi and theta? This is going to be, well, I'll rewrite it. F of g of theta, or of phi and theta is equal to, so z is cosine phi, and our x was cosine theta sine phi. And we just have a 1 here. Nothing replaces 1 except for itself. Okay, so now we have all of our components, right? So we have our normal vector here, our vector field in terms of phi and theta. And we have, oh, okay, one last thing. Sorry. We should figure out the bounds for phi and theta. That would be important. So here we have our hemisphere, upper hemisphere. So that means z is positive, right? So here's our upper hemisphere, and let's look at theta first. So theta starts at 0, and to go all the way around the circle, it has to go from 0 to 2 pi. Just a general rule, theta usually goes from 0 to 2 pi, unless the problem says otherwise. So, okay, so theta goes from 0 to 2 pi, and now we have to concern ourselves with phi. So phi starts up here, okay, so that's where it equals 0. So it starts at 0, and it goes down until it hits, and here is where phi equals pi over 2. And if you go any further, it's going to go out of our surface. So it stops at pi over 2. Okay, so now we have our bounds, and now we have everything we need to plug into the surface integral for the vector field. So I'll write 0 to pi over 2, and then 0 to 2 pi. So I did phi first and then theta, so d phi, and then there's a d theta in here. And those are probably too close. I think we're going to have pretty long stuff. So I'll write those at the end. Okay, so what we're going to have is we're going to we're going to take the dot product of this thing and this thing. So yes, there are going to be a lot of terms. Yeah, but let's get started. So we have technically this sine phi. It can come out in front since it's going to be in every component anyways. So I'll write that here. And then we have our vector field. So cosine phi, and then cosine theta sine phi, and then a 1, dotted with cosine theta sine phi. I'm going to try my best to squish this in. Sine theta sine phi. I'm not going to make it. And cosine phi. And then we have our d. Let's see, the order we have is, here is theta and here is phi. So we have to do, the inner one is theta and the outer is phi. Sorry I squished that in at the end there. And I'm messing up a d right now. Okay, so basically this is where we're at right now. And we need to dot all of this out. So I guess I'll try this on the bottom line here. So we have 0 to pi over 2, and then 0 to 2 pi. And, okay, so the first components multiplied together are going to be cosine theta, cosine phi, and then a sine squared phi. I'm accounting for this as well. So this here, times this, times this. Okay, that's what I just did there. And we're going to add that to this, well, I'll mark it differently. This times this times this again. Okay, so that's going to be a sine, well, yeah, okay. So sine theta, and then a cosine theta, and a sine squared phi again. Wait, hold on. That is not a squared, that's a to the third. So that's a cubed, because we have this one here. And the last one, what should I use for that? I'll use a check mark. So the 1 here, and the cosine phi here, and again the sine phi in front. That's going to equal a sine phi cosine phi. Okay, I think that does it. So we're here, and then d theta, d phi. So, just as a reference, theta and, well, yeah, whenever you have something, cosine theta, when you integrate over that on a full period from 0 to 2 pi, you know how the graph goes, well, for sine and cosine, whenever you integrate over a full period, so like here's pi and here's 2 pi, so sine graph looks like this, right? It goes above and then below the x-axis. So these two areas, the positive one cancels with the negative one. So the integral of sine over a full period is 0. And likewise, when you have cosine graph, so something like that, so we're going to start up and then we come down. That's not right. When we come down and then go back up, that is also these areas under here, they cancel out and give you 0 over a full period. So since we have this 0 to 2 pi, and we have a cosine here in this term, a cosine and a sine here in this term, for that matter, and phi it doesn't apply to, okay? This is just in reference to theta. But anyways, so basically what I'm trying to say is that these two terms here, because of the existence of theta, of cosine theta and or sine theta in each one, and because we're integrating over a full period, 0 to 2 pi, with respect to theta, these terms are going to integrate and give us 0. Okay, so all we have to do is concern ourselves with this last term here. Alright, so what we have left, and you'll see, I mean, like, you could work it out if you really want to. It's just going to be a lot of tedious work. But, so, anyways, what we end up with was a sine phi and a cosine phi, and then d theta, d phi. Okay, so here again we have an iterated integral, iterated. So we can solve it in steps, so that means we can group them together in parentheses. So I'm going to write the theta things, so 0 to 2 pi, 1 d theta. And then that'll be multiplied times the phi things. So the phi bounds are 0 to pi over 2. And then we have sine phi, cosine phi, d phi. Okay. So now here at this point, we can use u substitution. So I'll make u be cosine phi. U equals cosine phi. So therefore, du equals negative sine phi d phi. So getting d phi by itself, we get du over negative sine phi. Okay, so continuing to simplify, in the first thing, it's pretty simple. We get theta as it goes from 0 to 2 pi. Okay, so that's the first thing. And then here we're going to do u sub. So we don't have anything to sub in for the sine phi yet. And then cosine phi is now u. And d phi is du over negative sine phi. So the one on the bottom takes care of the one on the top. But then we get this factor of negative 1. So I'm just going to bring that to the front. And what we get is a 2 pi here, so 2 pi minus 0 times a negative 1 times the integral of u du, and that's just going to equal negative 2 pi, and then times 1/2 u squared. Okay, and this 2 here and that 2 there cancel out, so we just get the following. We have negative pi of cosine squared phi. I plug that back in for the u, okay, as phi goes from 0 up to pi over 2. Alright, so now we'll continue solving here. And we get negative pi times cosine pi over 2, and all of that squared, minus cosine 0 squared. Okay? And that's going to equal, this is 0, cosine of pi over 2 is 0, and this is a 1. So we get negative pi times negative 1, so that's just going to equal a positive pi. Alright, so that's it for that problem, and now we'll move on to something different. Now I'm just going to go over the concept of fluid flux. I kind of sort of vaguely referenced it, or alluded to it before, earlier on. So this is, well, okay, I won't give it away yet, but I alluded to it before by saying that in the upper hemisphere problem that we just did, imagine some kind of like air or water like flowing through the surface. So basically that's what fluid flux is. It's just giving an official like definition for it. So fluid flux is defined as the flow rate of something here they're apparently thinking it's something, this something is a fluid like water or air or something like that, through a surface. So this is measuring like volume per unit time. And if this is more of like a physics application, or you could think of it, if you're not like a very physicsy person, you could think of it as a physical application, like just to the real world kind of thing. Okay? So flow rate, so this fluid flux or the flow rate is going, these are the same thing. They're just interchangeable terms. So flow rate equals the double integral over the surface of V dot ds, or you could think of this as V, well, sorry, that was a weird V. V dot N, hold on, I'll write a capital N here, and then ds. These are just different notations. This means the same thing as that. Okay, but anyways, and then V, you might be wondering what that is. V is a velocity vector field. So what that means in a physical sense, I guess. So if V is your velocity, so that's your velocity of your fluid at a given point. So if you integrate the speed of everything going through, when you take the double integral, that's going to give you your volume per unit time. Okay? Alright, so again, I just wanted to clarify that D S arrow is equal to, whenever I put N ds, that's the same thing. I'm just referring to the normal vector. Anyways, okay, so that's it for that. And a final note is, let's say you take the double integral over some vector field, okay? So something like that, all right? So if you take this and let's say you get 4, okay, is your answer for some reason. So let's say you get that, but this is with, let's say the outward pointing normal, okay? So outward pointing normal vector, okay? So on the other hand, if you were to do the inward pointing normal, the notation for that would be a negative s here. This just means you're reversing the orientation. So reversing orientation, or your direction basically, of your normal vectors. And then, so that, in fact, is going to equal the negative of your previous answer. So that would just be a negative 4, okay? And another way to write this is basically in like more theorem-like form, even though I don't think it's a theorem. But anyways, so when you traverse your surface in the opposite direction, or when your orientation is reversed, so something like that, whenever you see something like this, you could just think that you're taking this negative sign and placing it in front there. You're sticking it in front of the double integral, and you're doing everything like you should be, right? So then here you can see that this part, remember we said that equals 4 for some reason, and then so this whole thing is going to equal a negative 4. Okay, so the takeaway there was that surface integrals, when they're the same, but you just traverse, or you reverse the orientation of one of them, then that'll just be the negative of your original surface integral. Okay, so that's it for this video, for this concepts video, and I'll talk to you later if you watch the practice problems video.
I feel my body